Maria, you can start. So greetings, dear colleagues from the INSAS network. And today we will attend to the webinar, second part of the webinar of assessing soil salinity and sodicity using remote and proximal sensing data. And this will be as well performed by the Dr. Elia Escudeiro of the University of California. And he is so generous and how to say, has the courage that will present us on live how he does with computers, dealing with data. All you, I guess, that have the experience that demonstrations in direct, they have some problems, but Elias Escudeiro is very well experienced, and I'm sure that this will not happen. And webinar will be clear and fluid. And as at every webinar, remember that you have the window for making these questions along the development of the webinar. Dr. Maria Kuniuskova will try to make how to say a merging of parallel questions for finally present them to Dr. Elias Escudeiro that will try to answer all of them. And remember that these webinars have the intention of training and capacity building, so do not hesitate to make your questions, and we will have time enough at the end of the webinar for that. And now, well, all of you, if you attended the former webinar or just if you read literature, all you know Dr. Elia Escudeiro. Elia, the floor is yours.
Elia, please switch on the sound.
It's good to make the mistakes early so that we can then get them out of the door. Well, thanks very much for the introduction and for having me here today for the second module. Thanks everybody for taking the time out of your busy schedules to come and take a look at some of the case studies that I'll present today, mostly on mapping soil salinity. Just a little bit of a disclaimer. These are at the level of perhaps like master student level or like advanced undergraduate student. So they're directed to showcase how to deal with this type of sensors data for people that are not that don't have like a very high statistical skills and so on. Okay, look. So for those that didn't attend last week, I'm calling you from the southern area in California on the southwest of the United States. The University of California Riverside campus is here in the south, in close to Los Angeles. We serve agricultural areas that are of primary importance for the United States as well for global food production. I'm calling you from my second affiliation from the building of the U.S. Salinity Laboratory. As detailed last week, this is the National Laboratory for the United States Department of Agriculture for basic research on chemistry, physics, and biology of salt-affected soil, plant, water systems. Today's talk and last week's talk are authored by myself, Todd Skaggs, Dennis Corwin, Sharon Benes, Nan Lee, and Ali Mortazar. The contribution of other former employees, postdocs, students, visiting scientists were acknowledged in the slides last week. and if present this week, they will be acknowledged as well. So last week, we talked about an introduction of soil salinity and sodicity. We talked about proximal sensing techniques and methods to map and monitor salinity and sodicity at the field scale, how that's a very good tool to get very accurate and quantitative maps and a monitoring tool. We talk about the great benefits that come from the use of remote sensing technology for detecting soil salinity, especially when used at very broad scales. We talked about challenges, future directions, and soil salinity and sodicity monitoring. And then we show some examples of implementation of sensing technologies. So today, we're going to take a couple of those examples and look at how the data is analyzed for making salinity maps. So we're going to look at primarily two examples, one at the field scale, using near-ground sensors to map soil salinity, and then the regional scale salinity mapping example with remote sensing. We'll have a data analysis walkthrough for the field scale salinity mapping example using Microsoft Excel and Esri ArcMap. Whereas we'll take a look at pretty much a slideshow on following the steps and the key aspects of a remote sensing broad scale example from a paper from Whitney et al. From 2018. One notice here is that these, as I said, these are fairly basic examples on data analysis and data handling. This can be done, of course, with other software, including free software as well. We nowadays use anything, but every platform has a pros and cons. And obviously, I'm not going to cover the pros and cons and review each tool here. I'll just give in this the reference to these two software just for the benefit of the audience, not really an endorsement of either of these tools. So let's get started. Single field salinity mapping. I'm posting here some relevant literature. It's just to get started for, especially if there are students in the audience or people that want to read more to get into it. These are papers that should be accessible, found on online repositories, even if you don't have a subscription to the different journals. If you cannot access them, you can email me and I should be able to send you a copy. The first off that describes the general protocols for field scale mapping with the apparent electrical conductivity is a paper from Dennis Corwin and myself. Second paper that talks about once you have the sensor data, how do you select the samples and the locations where to go do your ground truthing. Great work from Scott Lesh, former US Salinity Laboratory scientist from 2005. And there's a whole field of literature that follows and precedes this paper, as a matter of fact, on using ordinary least square regression for spatial prediction of soil properties. Great overview paper from Scott Lesh and Dennis Corwin from 2008 from Geoderma. So we saw this last week as well. The procedure that we generally use when we are looking at mapping salinity at the field scale involves using geospatial soil sensor measurement of apparent electrical conductivity collected with high accuracy GPS, generally in the 10 to 30 centimeter scale. Definitely you want to be under 50 centimeter scale for accuracy. and then driving around the field and collecting the data and use that information on spatial variability to direct the soil sampling, and then later on model salinity. So in this example that we're going to see today, it's a 32.4 hectare in San Jacinto, California. So it's a dairy farming area that is 30 or so kilometers south of Riverside, where I'm calling you from. Here in this example, we collected thousands of apparent electrical conductivity measurements, and we are discussing. I'm showing here the 0.1.5 meter soil profile, but we're going to discuss the 0.75 meter soil profile measurements for the example. Then this variability of the sensor helps us identify representative locations where to go sample the soil, which is collected, taken to the lab, and where the salinity of these samples is measured. And then we develop linear models using ordinary least square methods to estimate salinity everywhere we have a sensor measurement. And then spatial interpolation is used to map salinity over the entire site. Before we take a look at the actual modeling and like how the data is handled, we need to do a little bit of a dive on some of the rationale for using this type of models. So we are trying to map salinity, defined here as the electrical conductivity of a saturated soil extract, ECE. We defined it in last week's webinar in detail. And then we are using near ground sensor measurements to map salinity. And that sensor that we're using is the apparent soil electrical conductivity, ECA. So since the 50s, scientists have been describing the relationship between apparent soil electrical conductivity and salinity, water content, soil type. And one of the laws that described it in the a fairly accurate mechanistic fashion is Archie's law, which describes ECA as a function of the pore water conductivity or pore water salinity, the soil porosity, and the relative saturation. And then you have several fitting parameters that are dependent on the soil type, particles, pore distribution, density and geometry of the particles, organic matter content, and so on. Meanwhile, I'm sorry if there's a little bit of noise in the background. There are people working outside the building, not under my control, unfortunately. So this is basically a function that ties ECA to pore water salinity. But the pore water salinity can generally be expressed as a linear function of the total ion content in the soil. Salinity as the ECE then can be tied linearly to ECP, of course. And so we can express ECA as a function of ECE. And here, this can be done reducing Archie's law or the model from Rhodes et al. Or similar models by having ECE as a multiplicative error model that is tied to ECA, where you have soil parameters and a multiplicative error component. If you excuse me, I'm going to try to get the people to stop banging on my window. Yes. Apologies. after a log transformation of this model, actually, I'm going to try to, because you should not be hearing the noise. I apologize for this, but this is not working for me. They're keeping on banging on the wall. I'm going to try to talk with this also. Noise should be reduced from my end.
We do not hear.
You do not hear the, yeah, it's good because Zoom has the noise reduction function. I'm sorry for interrupting this, but they are washing the windows outside my office and they're banging like very hardly on the window, and I'm right here. So yeah, but with the headphones on, it's much better on my end. So apologies for the interruption. Yeah, so we can use a log transformation and have this multiplicative error function become a linear function, where you have ECE that becomes like a traditional linear model where you have an intercept, a slope, and your explanatory function, and then an additive error. So because of this, we can then parameterize estimate this relationship using ordinary least square. But we need to make sure that the underlying assumption of this type of modeling are respected. So residuals being normally distributed, and what's more important, which is not often looked at in ordinary least square when you don't have spatial data, the errors need to also be spatially independent. And this is very well described by that reference from Lesch Corwin from 2008. So before we do the actual modeling, we need to get the data from the field to use as a ground truth. So once we decide that we want to work with ordinary least square modeling, we can then select an adequate sampling scheme for ground truthing. And what we do basically is that we need a representative subsample where you have, say, a survey with thousands of sensor measurements and a small subsample of that survey that needs to have the same average and standard deviation and such. And then we also need to have it so that it supports the chosen modeling approach. And in this case specifically, the points should be as far apart as possible from each other, so that we don't have autocorrelation on the model residuals. So this is generally done on our end by using the ESAP response surface sampling design software, which is a very old piece of software. It's still available, can be used. It's very fairly straightforward. It does require a little bit of tweaking with the current versions of Windows to make it work. And I'm kind of sorry that we are having this webinar today and not early next year, because we are in the process of releasing the newer version of the software, which should be out with a peer review publication first in the next few months. Okay. So we decided to use ordinary least square, and then we have a model that where your dependent variable natural logarithm of VCE is a function of intercept, and then you can add as many predictors as you have in terms of the electromagnetic induction sensor of the ECA. In this case, in this example, you have like the vertical component or the horizontal component of a specific sensor, and then the random error. So you need to have random error and spatially independent error. If you want to check that, we are going to check it using tools such as the Morang-I for spatial autocorrelation. We're not going to discuss this because we're not going to see this today, but occasional autocorrelation can happen, and then you need to correct it with by adding some trend component. You can use the geographical coordinates at the field scale to have an empirical trend component removed from the data, or you can use different type of modeling interpolation, or parameterize the model in a way that allows you to have some bias in your residuals. if you have a lot of sensors from your field, you may want to use principal component analysis scores as explanatory variables so that you avoid having extreme collinearity in the explanatory variables. So after this overview, we can finally take a look at some examples. And we are going to move to ArcMap to take a look at the data set at hand first. Here we go. This is the field that we were looking at earlier, about 32 hectares of forage crop here in Southern California to support the dairy farm industry. Here we have thousands of measurement of ECA, and one of the first things that we do is to take a look at how the ECA data looks. And again, we are taking a look at the horizontal component. We're just going to look at maybe like we can do quantiles just to get different. Okay. Here. And this blue to red, where blue is low and red is high. And again, this is a proxy for soil salinity. We are expecting it to have a relationship between salinity and ECA. So we are expecting this area in red to have higher salinity, and these areas in blue having lower salinity. There are several papers that tell you how to pre-process the data. Perhaps you might want to remove areas from the edges where like you're measuring compacted soil in the roads. You may want to remove outliers and so on. But if you're happy with your data, you can proceed and use these for the determination of your sampling locations. And in this case, we have these 20 locations that represent the spatial variability of that sensor data that we were just looking at. And here we have a set of coordinates, the sensor measurements. We have like the other statistics that I used back when I worked on this data. But what's important is that once you have the values for the sensors, you can also add, once you have completed the laboratory analysis, the values of salinity measured in the laboratory, which is what we are going to look at now. So hopefully this is zoomed in enough for everybody. But what we were talking about earlier is that, yeah, we are going to have one predictor, that is the ECA, and this is the horizontal orientation of the sensor that we use for that specific survey. So it relates to the 0 to 75 centimeter soil profile. And you can see that values here, we have a minimum of 0.14, maximum 0.88, 20 locations. At each 20 locations, we have soil salinity for a certain depth. I believe this should be the first meter or first 1.2 meters. And you can tell that there's also variability from 0 to 6.4 to 4.38. So it's in the non-salt affected to slightly affected ranges of soil salinity. So the first thing that we do, obviously, is to take a look at relationships, just to make sure that everything looks as expected, that there is like an overlying relationship between what's in the x-axis here, that is the ECA, and the y-axis, that is the ECE. So there seems to be a relationship there. And another thing that you may wanna have, especially if you are trying to develop a regression model to calibrate the entire survey at the field scale, is to say, if you have, let's say, let's see maybe like a very high value here. This is one instance where having outliers very far away from your data cloud really counts as having an error in the data set. So if the error is in the soil side of things and the time allows it, generally we suggest to go back and do the analysis in the lab for the soil again to confirm that the values was perhaps like due to a laboratory error. But if the error is in the sensor data set, generally there's not much that can be done. Maybe if it's like one specific point that has a mistake in the data set, we can go to the nearest neighbor and get like a different point. Or if the point then needs to be eliminated, they might have to lose a point in the data set. But generally speaking, this is the time when you want to make sure that the data set that you're working is a very good representation of the system that you're trying to model out in the field. So we talked about converting this relationship into a linear relationship using natural logarithm transformation. So we have the natural logarithm of ECA and natural logarithm of ECE. And this is, again, this is your Y and this is your X in your equation. So we just use the function for that in Excel, which is pretty neat, and we can use it all the way down for the entire data set. So once we take a look at this graph again, like in here, we can take a look and already this looks a little bit more straight as a cloud than it was before. So here, yeah, we got it all here. What we generally do in Excel is that we use the different functions that Excel has. You may use the LINEST function to have a regression calculated with all the parameters of the regression, the standard errors, the F statistics, and so on. For this specific use today, we can use the data analysis tool and the regression package, which is equivalent to that. And we have a Y range that is over here, and this is the X range over here. We have labels, and we want to output it perhaps over here. Okay. So in this regression, we have R square of 77. But what's more important is that the whole regression is significant, and then that we have the coefficients of the regression. And what's important really, it's the slope of the regression that is significant. Once we verify this, we can look at the residuals. So we have observed, we first need to predict, excuse me. Of course. And the prediction is fairly straightforward. We use the intercept plus the slope, and I'm locking these values so that they can be used for the entire column, multiplied by the explanatory variable. And then, of course, that's okay for the whole data set of 20 samples. And one thing that you can do here, obviously, is you want to see if these values are on a straight one-to-one line. And we're taking a look a little bit later on how to create a graph like this. But once you have this, you can have the residuals. And this is like still it's a natural logarithm transform, and which is where you want to test all your modeling assumptions, of course. So observed minus predicted or minus estimated gives you the residuals. So one of the things that you want to make sure is that you want to have a graph of the residuals versus the predicted, and that should be showing that the residuals are from low values to high values are equally distributed above and below zero. So you have like a zero residuals, 0.6 and 0.6. So you have a fairly equal like analogous distribution of the errors in the positive range and in the negative range. Another thing that you may want to do is to check if the errors have a visible correlation with the coordinates to indicate a spatial structure in the errors, which we don't see clearly here. And then a more sophisticated way that you can definitely not do in Excel would be to go back to ArcGIS and take a look at import those residuals as a shape file, and we have them here. And use a tool like the Moran Eye and to understand if this data set as a spatial structure that can be deemed as autocorrelated, or if the distribution is random. So one of the good thing about let me see if I want to make sure that I'm not sharing things that I'm not supposed to be sharing. Apologies for that. Okay, I'm just gonna open these now. One of the good things about ArcMap and other software is that they allow you to interpret these results in a fashion that that is pretty straightforward. Let me just show. Excuse me. There you go. So we are looking at here are the results of the Moran's IE index, and it tells us that this data set has a random structure, so that the values don't have a spatial structure. If we had a spatial structure, then we would need to take care of it by doing the suggested steps from one of the slides that I showed earlier. So we confirm that we have a good regression model. And now it's the time to leave the natural logarithm space and go and back to the back transform space. So we want to estimate ECE from here. And here, basically, we will just take the values in the natural logarithm and we elevate by E. So now, finally, we can take a look at some observed versus predicted relationships in the real like data space, in the back transform space. And here, excuse me, we want to have the predicted values, excuse me, in the X, and the Y will be our observed values. Yes. Okay. So we have predicted soil salinity on the X. ECE. see. And then we can, it helps with having the same scale on both X and Y axis. So you can look at the one-to-one line and make sure that that you are on it with your data set. As a matter of fact, you can even add it as a data set here, 0 to 5 perhaps, and we can just do this. We can add another series. We can call it the one-to-one line. X values and Y values will be these, right? Okay, and we can make it be a line data set. Maybe not as thick and dashed, let's say, yeah? And no markers. We don't need those markers. We're good. Let's put this from 0 to 5 as well. And 1 decisimas per unit increment. Of course, I forgot to add the units here, but they are in decisimas per meter. So one of the things that you may want to do is to look at the R-square of this back transform relationship. And the tool that we are going to use is the R-square function here. So we can use the, it's in this case, X's and Y's is equivalent, but we said that we want to use the predicted or as a Y, and the X's is the, well, the other way around, but that doesn't really matter. Excuse me, I made a mistake. Okay, now it helps when you can see. Okay. So this is the R-square of your regression line. And as a matter of fact, if you add it on here, you see that pretty much is the same. And also it tells you that the observed value is equal to the predicted plus minus an error. And it's you want this number to be as close as possible to 1. One of the things that you want to calculate here might be the root mean square error and the mean absolute error, because those are matrices that can help you, once you do a lot of these surveys, put these calibrations onto a reference of like how accurate they are, and if they are accurate enough for your specific use. So to calculate the root mean square error, first we need to calculate the quadratic error, which is equal to the observed minus the estimated square. And to calculate the root mean square error, let me see, we just do the square root of the average of all of these errors. 0.47, 0.48 as a matter of fact. And then the mean absolute error will be the average of the absolute errors. Okay. Okay, doke. We have the error, which is basically the residual, one minus the other. As a matter of fact, I forgot to add formula for this in the front, which is in Excel would be the ABS for absolute value in English, in the English version. And there it goes. For the mean absolute error, we want to do the average of all of these values. And that's about it. you may want to reduce this to a fewer decimal digits. A reminder that this is in Siemens per meter, same unit as the variables that you're modeling, and the same goes for this other one. So if you're happy with the results that you're having, and we are in this case, we can take the values of our regression, and we can move now, instead of working with the 20 sites, we can work back to the full survey of the sensor data set. And that's, I have like a crop out of that over here in the second sheet of this example, where you have like the ID of the single sensor measurement, the coordinates, and then whatever else is attached to your survey. In this case, we just keep it simple. We have the sensor variable that we were using. And here, well, we'll just add the values of the regression on the side, and we can do ECE, and we can put like like estimated, right? Like we just the estimated one. So we just calculate these at every location where we have the sensor variable by applying these regression coefficients. So the intercept plus the slope of the regression multiplied by the predictor, which is our sensor signal. And basically you can calculate it everywhere. Once you have this calculated everywhere, you can import this as a new shape file in your ArcGIS, or like a geo database in R, or wherever you're doing this analysis. And I have it already here for our convenience, where I already added it yesterday, or preparing for this example, and we just want to look at it real quick. Let me close this. Let's take a look at it. And there we go. Here we have the salinity estimated at every single point where we did the soil sampling, the soil sensor survey for this entire site. So here we have so many data points that actually it's pretty, like the map is very evident already. But let me zoom in very, very like at the survey level, and let's just measure for a second. So all these points are 3.5 meters. This is a very intense survey that we did. This is like 6.6 meters apart and so on. So, but it may happen that you have surveys that are not this dense in terms of the sensor that you're using, or you may want nonetheless to have values of salinity estimated everywhere in your site, right? So one of the ways to do this, let's first zoom back at the level of the single screen, is to use a geostatistical approach. And in this case, we can use maybe inverse distance weighting when we have this much data, but kriging, of course, can be also used. So I'm just going to select the default. I like to use this 4-sector with 45% offsets. And then nowadays that we have good computers, we can also up the number of samples that are considered in the calculations. But that's not, I mean, when you have this many points, it's not really a big deal. And one of the things that you want to make sure is that your leave one out cross-validation lands very well on the one-to-one line. So if you're happy with your interpolation, and we are in our case here, then you can have a map that estimates salinity everywhere on the site. One of the things that you want to do finally is to export this as a raster, because this will allow you to place it on a grid that is typically, you want it to be at the same resolution of your decision-making process. And in ArcGIS, one of the things that you can set up is the processing extent. And as a matter of fact, if you have a reference satellite image that you want to snap this salinity map on, you can use it by adding that here. I'm not going to do this now, just in case it requires too much computing power, because ArcGIS is always unpredictable in that sense for me. Okay, we look at how to go from sensor measurements, take the soil samples, calibrate a model, and it's a lot of work, but at the end of the day, we have like a map that is very accurate and we can make informed decisions on. You may wonder, okay, I've done this work for one field. Can I use this regression model for other fields? So here we have two fields that are not in the same farm, but nearby, where we have the sensor measurement and salinity. And we can tell already that at these two sites, there is relationships that are, this site is definitely stronger than this other site, but they already are not overlapping, kind of suggesting that we might not be able to use the same regression model to model salinity at the two. But as a cautionary tale, we can take the values of the sensor of the regression from this other site that we just looked at, and we can estimate ECE based on the model, the linear square model from the other side, from independent side, right? And it's done as we did it before. The slope, the intercept plus the slope that multiplies the predictor, and the same regression for the entire data set. Okay, now let's take a look at the observed versus predicted at this site. Obviously, we are far away from, excuse me, let's do as we said earlier, let's put everything in the same scale here, although we should put it, excuse me again, should put it at 10, I think, because that's the maximum salinity that we observed in this data set. So we are off the one-to-one line, that is the desired output for any modeling, correct? And as a matter of fact, let's take a look at the two sites together. So this is, I'm going to move down to the second site with the other data series. So we are in both cases pretty far off in terms of like how the model did away from the desired one-to-one line. So this is a cautionary tale to say these type of models are very powerful at the field scale, but because there are a lot of secondary factors that are influencing the measurements of apparent electrical conductivity at the field scale at the moment when the surveys are done, this type of empirical model should not be used, extrapolated at other sites to estimate salinity. And this is also another cautionary tales that tells that these measurements should always be calibrated to salinity with some sort of modeling approach to have a quantitative indicator of salinity, because otherwise they might give you spurious indications of what the salinity levels are. Because, for example, again, this is the ECA. So at 0.6 decisiemens per meter, here we are around, let's say like 2.5 or so. Well, like in this data point, we are 2.3 salinity at the decisiemens meter salinity level. In this other side, with the same sensors and everything, the 0.6 corresponds to a much higher salinity level. So I believe this concludes the examples at the field scale. And in the next 10 to 15 minutes, we're going to take a look at step by step what was done in a proof of concept by Whitney et al. In 2018 on the use of MODIS time series for salinity assessment over California. And as a matter of fact, that is based and is a continuation of an excellent piece of research by Zhang et al. Out of China, that were the first one trying to saying okay, if we want to use MODIS, maybe the time series vegetation index data is the way to go. And let's review the paper and their primary findings. As a matter of fact, they used time series of MODIS to determine, they call it parameters with ecological meaning. From from a crop science perspective, you might talk about phenological stages of parameters that are indicators of the phenology of a crop. Start of season, end of season, amplitude, the length of the curve, the peak value, left or right derivative, and the seasonal integral, which is what they use in the paper. And each of these can be calculated or defined at the data science level, but also what is important, what I think what I wanted to have these workshops transpire is that please make sure that, what I suggest is that you do try to keep a foot on the actual ecological or agroecological processes. So this seasonal integral is has the ecological meaning of the sum or accumulation of seasonal photosynthetic activity, and it's related to the biomass or net primary production. So here they use this indicator, and nowadays in my lab we are using R and Python packages that are available for extracting the phenology parameters from this vegetation index time series. And there are several out there, and they are, they work fairly well. So what they observed is that if they use this seasonal integral data, they have a very good correspondence between those values over here, seasonal integral data, and the salinity measure on the x-axis. But they were noticing that the crop and wasteland that has allophytic crops and the mixed pixels should be treated differently, modeled differently. But their observation was based on the fact that, and this is the example for the crop pixels, when affected by salinity, this seasonal integral or the curve would be smaller in highly salt-affected areas and slightly bigger in moderately salt-affected areas, and in not salt-affected areas or lowly affected areas, it would be much, much greater. But one of our observations that we also discussed last week is that these differences in vegetation performance over a single season could also be determined by limiting factors other than salinity, right? So water stress in a specific year or mismanagement of a specific crop and so on. So we took this first milestone by Zhang et al., and we tried to say, what if we use a multiple year time series instead? So we move on and talk about the paper that Kristen Whitney, a former PhD student that I advised from Chapman University, which is a university out here in Southern California, on the use of MODIS time series for soil salinity assessment over agricultural soils in California. This uses 500-meter resolution, which is primarily aimed at monitoring landscape level processes over broad scales, but it's probably too coarse, as we discussed last week, for directing agricultural management practices at the level of a single field. Obviously, nowadays, even back then, we had different satellite products such as Sentinel that is way more useful for that specific purpose of field scale management. If you go with the smallhold farms, you might want to go to even higher spatial resolution satellite data. But the same methodologies that we are looking at today, or we discussed last week, are going to apply for those applications as well. So in here, we used 22 field samples in 2013, 550 hectares in the Western San Joaquin Valley, which is the area with most of the salinity problems in the Central Valley of California. We have 73 MODIS pixels with soil salinity information. And we have different ranges of ground truth pixel coverages. Of course, because of the like large pixels, some of the pixels were like fully covering a field. Some others were covering field and a neighboring field as well. And in a specific case, we had a field that we discussed last week as well, where you have like the ground truth site, which this one in blue, that is extremely different, has an extremely different management from surrounding sites. And this type of mixed pixel is was clearly an outlier in the data, and we removed it. So we took a look at visible and near infrared vegetation indices from MODIS, NDVI being one of those, EVI the second, and the one that we developed that works very well for arid and semi-arid areas, the Canopy Response Salinity Index, CRSI. They all meant to look at salinity through the performance of the vegetation over the salt-affected soils. They don't look directly at the soil and at its salinity. So what is done in this case using time series is that you may have data and you may filter it out for like non-cloudy data sets. And at each pixel, you have a collection for the different years. Oh, excuse me, I'm still not using the presentation mode. I apologize. You may have hundreds of available scenes or values in a pixel that are not in a continuous fashion that allows you to calculate phenological parameters. And here we smooth this time series. In a specific case, we use the Savitzky-Golay filter to interpolate this time series at the pixel level, so that then we can use these to calculate the seasonal integral, which is in this case goes from, I believe, the start of season and the end of season. So in this case would be like this curve here. And in the case of multiple curves, it would be the integral of like the entire vegetation growth over that site. So what we observed is that we calculated this seasonal integral, and for all the three indices, but CRSI is the one that performed better. So we're just going to focus on that for this discussion here. But what we did is that we said, okay, let's look at the correlation between this seasonal integral and over the entire data set and the salinity for the single year when the soil survey were carried out, or for the maximum value at the pixel level over 2 years up to 7 years. So for this specific data set, we observed that the single year was clearly outperformed by using multiple years. And in this case, 2 years were sufficient to have a good predictor of soil salinity. So once again, if you have, going back to the previous slide, if you have season 2013 and 2012, you pick the maximum value of seasonal integral for those 2 years for the single pixel, and you use that as the predictor for your salinity. So because we had data with different pixel coverage, from 25% pixel coverage to all the way up to 75% pixel coverage, we developed a model here that was a weighted regression that keeps the pixel coverage in account when doing the regression. You wouldn't have to do this if you were working with high resolution data, of course. And we, similar to what Zhang et al. Did, we did a mixed model approach where we have two different regression basically for the two type of landscape that we have. So the cropped irrigated landscape and the fallow landscape. And similar to what Zhang et al. Observed, we have a very strong linear correlation between the cropped pixels between these CRSI integral for the 2-year maximum and this observed soil salinity. And we have instead a nonlinear relationship between the salinity and the 2-year maximum CRSI integral for the fallow pixels. So what we learned from that and through this data analysis walkthrough is that the phenology indicators provide a better information than raw data and single date. And that's what was shown by Zhang et al. And we showed it in our manuscripts that we wrote on these topics. This one that we looked at here and is also confirmed by other papers in the literature. We found out that multiple year remote sensing data set provides stronger correlation with soil salinity than a single year data. In all the cases that we looked at it, of course, there might be some other cases that where that is not the case, where might be lucky that one single year is good enough. We observed that the strength of the correlation coefficient between vegetation indices and salinity were generally ordered as CRSI was the stronger predictor, then NDVI was the second stronger, and EVI was the third stronger. But this is expected to be region specific. And in fact, Zhang et al. Had like different results, if I remember well. Then the spatial resolution of MODIS is not ideal for field level salinity assessment over California farmland and other land with the similar short scale variation of soil salinity, agronomic practices, and land use, but instead is useful for broader scale, landscape level scale analysis of land use change and land degradation change. With this, I concluded the data analysis example and walkthrough for field scale and remote and broad scale salinity mapping using near ground and remote sensing tools. Thank you very much.
Thank you very much, Elia. And now Dr. Koniuskova will convey to you some of the questions that were made by the participants.
Yeah, so if I may use my position of being here, first I would like to ask the questions that I have, if you allow. So first, my question is how did you choose these 20 points? Why 20 and where? So it's a logical question, always coming from the ground truth data selection, but still, what was your approach? Just to tell us.
Yeah, so we went through it very briefly, but it's a topic that would take like a whole day to go through, or more, as a matter of fact. This paper is a good start for everybody to read upon it. The use of response surface sampling design for sensor-directed soil sampling. But briefly, we used it using the, sorry for scrolling here, using the RSSD software from USDA, and this link will take you to the download page for that software. The concept behind it is to support ordinary least square modeling, so that you have, as I said earlier, a representative subsample. So you're, in this case, N40, but in the other case, N20, where you have the samples that you select having the same statistical properties of your entire sensor survey, but at the same time, dispersed in space enough that they are not going to lead you having autocorrelation on your residuals of the regression. So why 20 though? So here there are 40 in this example that we are looking at here, and the other example they are 20. In other surveys that we do nowadays, because we deal with like big data sets, we generally do 12, as a matter of fact. Soil sampling is very expensive. That's the bottleneck, because ideally you would sample these in thousands of locations, right? Ideally, you wouldn't use the sensors to start with. You could just go and sample soil everywhere. But obviously, as a practitioner, farmer, we are dealing with the real life costs of monitoring soil. And one of the bottlenecks, of course, of the soil mapping enterprise is to reduce the labor cost and laboratory costs. And by selecting fewer samples, with the statistical approach that allows you to select representative samples, that's one of the ways to reduce the costs. So this ESAP software that USDA developed as a matter of fact, 20 years ago, and we are soon to release the second, like the newer version of the software, allows you to select representative locations and gives you the opportunity to select from 5 to like 20 or 40 locations, so that you are like you get a trade-off between expected accuracy of a model or the amount of money and time that you have to spend for collecting the soil samples.
Okay, thank you. The second question of mine was about this, about 20,000 readings that you have from AMI. Just to describe briefly the mechanics of how you make automatic retrieve, how do you automatically retrieve this data, because I understand that you don't measure each of these and just write down or whatever. So, and is it possible? So, do you buy it like one set of device, or you can do it yourself? So you buy a device and then you somehow connect it with your laptop or smartphone. So can you tell our
this is a very good question. Thank you so much. So in this case, this is the older rig that that was used, and as a matter of fact, this is what was used in the example that we had. What we see here, this is a spray rig that is used generally for taking care of pest control for crops. But we customized it, the Salinity Lab customized it for apparent electrical conductivity measurements. So you have a non-metallic tail here that hosts the electromagnetic induction sensor that is under a blanket for like repairing it, shielding it from direct sun. But what you will see here on top is that right above it, far away so that it doesn't interfere with the sensor readings because it's metallic, there's a GPS receiver. Nowadays, we have GNSS receivers with correction. In my lab, we are using corrections with lower than 10 centimeter vertical and horizontal accuracy. But each sensor measurement is paired with a coordinate that then allows you to map it. But as you're driving this, I use an ATV, like all-terrain vehicle nowadays. With this is a very, very old piece of equipment. Yeah, but a tractor, a pickup truck, even walking it, because sometimes we walk when we can drive in the field. You collect with a data logger every second, depending on the speed that you're having. Generally, we suggest going at 5 to 8 kilometers per hour maximum, so that you don't have drifting in your data. But as you're driving, you can just collect data, and if you collect it every second, you will end up having quite a few sensor measurements in your site. So nowadays, at least here in the States, there are several models, like commercial models that are used. Some soil scientists straight out own these pieces of equipment, which as Dr. Jorge pointed out very well last year, because the patent limitations for a lot of these sensors are now over. There's a lot of companies that are producing cheaper sensors than like the mainstream commercial trademarks that were like in the past used. So we are nowadays, for example, using an instrument from an European manufacturer that is cheaper than $5,000 to buy and operate. And that allows you to map salinity, apparent electrical conductivity on the go, fairly reliably. Obviously, the research grade sensors that we use go up like to like $70,000, $80,000, but you can also like make it very cheap. So you have soil scientists that own the sensors, and map this for in their service, and then they provide the maps to the farmers. We have big farmers that owns thousands and thousands of hectares, very big operation that have their own soil scientists with their own machinery, and they operate their own sensors. So the other thing is that these sensors work very well for very many years. This specific sensor was from a Canadian manufacturer, and we retired it only because it couldn't pair anymore with like the newer GPS units that are nowadays in the market. But the sensor itself was still working quite well. So if you buy one of these sensors and you treat it well, and you ask your students to treat it well, to treat them well as well, you will see that this can last for a very long time. So you can, make that initial investment type of inconsequential over the lifespan of the sensor. So at the end of the day, if this becomes like over the lifespan of the sensor not so expensive, the expenses that you want to reduce are the ones for soil sampling and laboratory data analysis.
Yeah, and so here, just to sum up for our participants, that the full package includes not only sensor. So here we have, if you want to measure like thousands of ECA measurements, so it's a sensor, then GPS or GNSS, then something for automatization, something where it's connected to laptop or it's like a tablet, and the car. So four in one.
But so I don't show it here, but we also walk the sensors, right? And then in those cases, instead of having thousands of measurements, you might end up having hundreds of measurements, which are still like good, and then you can use interpolation methods to have the map over the entire field. So whereas you can see that there's a power probe here in this tool, but like in most cases, we still go with a good old trusty auger to get the soil samples out of the field into the lab. So one of the point is that we mentioned high accuracy GPS units, because not only you want to have accurate georeferencing location for your sensor measurement, but once you're going back to take a soil core to ground truth or calibrate the sensor measurement, you want to be in the exact point where you collected the sample. So you need a GPS unit that will take you back to that sample, and we use the same in most cases, and that's why having high accurate systems will lead you back. Because one of the sources of errors is like the location or like not being able to repeat the geolocation of those measurements over time.
Mm-hmm. So last question of mine was about this ground truth data. So the measurement of ECA, which you compare, you compare the parent electrical conductivity and this ECA, and you are talking about 1 meter. But I suppose that you take a core, right? So did you make a mixed sample of it, or you measured for different depths and then you made the average value? So please tell us how you made the measurement for laboratory 1 meter soil.
So here is like a more of an agronomic decision, right? For like the expected root depth or where you want to map salinity. In this specific case, in the protocols that we recommend, and it was like I talked about it last week, and I'm going to repeat it now. We generally suggest to go well beyond the root zone to have like a good measure of the entire soil profile. So in most cases, we dig down to 1.8 meters, 1.5 meters, as much as we can go for the core. But we do this in intervals of 30 centimeters. So for every 30 centimeters, a soil is watered and the sample is created and then taken to the lab. We measure the water content at the time of the sample, and then we do all the laboratory analysis as well. But then if you want to create different soil profiles, you just average the single depths for like the 0 to 1 meter, 0 to 2 meters or so on.
Yeah, so here for 1 meter, you have 3 samples at least, and you take the average,
Yeah.
right? So you just take the average value for this 1 meter.
Yeah.
Okay.
So the typical, I mean, that depends on like the soil, like you need a little bit of a preliminary knowledge on the type of soils that you're working with. Lately, we are working with like our procedure in the field goes to 0 to 10 for the first sample, 10 to 40 for the second sample, and then 40 to 1 meter for the third sample. But previously, we have a lot of publications where we do like the 0.3 meters interval.
May I clarify something to Maria and in general interest? Now that you have several depths sampled, and with the measurement, let's say vertical and horizontal in most devices, it's a pity that you just give an average because you can make layering. So you can give an approximation of the electrical conductivity at every depth.
Yeah. Yes. So like the procedures are pretty much the same for the every depth. If the audience remembers, last week we had an example where we show the change over time for a field over 10 years, and there was one example that tracked the changes for each single depth. But at the same time, there was another example that looked at cross sections of the field and could see the change over time for at the different depths. And that's exactly how you do it. You would calibrate different depths and create models for the different layers so that you can look at the upwards or downwards movement of salinity as a response to different management strategies that you may have. But the underlying methods used for those are very similar to what we talked about today. So you would have like a response variable that is your target layer, and predictor variable that is like the one sensor measurement of all this or all the sensor measurements that are available to you, and then you would map the salinity assets at the target layer.
Yeah. So then the next question is about the outliers. So I would say that, yeah, so there are 2 questions which are related to this equation, to this linear equation that you have. That first is this always, is it always linearly related, this ECA and ECE, or it depends on the field parameters? So linearity, is it always happening? And the second question I would say that it's we can put them together, that if the outlier is a true value, so which means that you should create another function and it will give completely different predictions. So can you answer this question?
Sure. Well, so let's start with do we expect this to be always linear? So we took a look at the derivations of these models. We are kind of fortunate or based on the assumption that there is a physical law or a physical relationship that is expected between salinity and the sensor measurement, right? Which is the base of why all these sensors were developed in the first place, because they are useful to map soil properties and soil processes because of the expected relationship. But as shown here, this is not like a straightforward, simple relationship, of course. So there might be other processes that are influencing the sensor measurement. And do we expect a linear relationship between ECA and ECE? Always. I mean, that's pretty straightforward, but it might not be apparent in the data that we collect because of the presence of other structures in the data given by other soil properties present at the site. So once this model is fairly well it's an educated guess that you would always have it, but it might be non-observed because of other secondary influences, different soil structures, and so on. So in that case, it means that the tool that is used, ECA, with this resolution or the footprint that is used, is not really either mapping like ECA over the vertical profile because of like a heterogeneity in the vertical profile, or spatial structures of the soil type, soil texture, other influencing factors that are predominant over the salinity distribution. So obviously, that's because you might have these confounding factors. That's why we suggest, and we took a look at, always collect the soil samples to calibrate the ECE. So if you don't have a relationship that is clear and evident, one of the solution is, and if you need an accurate value at the site, there are several things that can be done, and that goes also for like the outliers that are real values, right? Collect more samples so that different models can be used. You may use regression kriging, very powerful tool, or like co-kriging or other models that are more sophisticated, but require way more soil samples to be taken for calibration.
And excuse me, I think that salinity usually behaves a regionalized variable, and this is just a survey. But you can have hotspots, and you can have sinks as well. So these layers could be another population, maybe, and then they deserve a special attention. But these do not. Well, this interpolation, it is complex because sometimes you have some drifts by external circumstances and so on. And I think that Dr. Scudeiro has presented here the basics, but the reading of the papers is highly recommended because they give much more depth into the complex aspects. Thank you.
Yes, of course. Yeah. So the overall message here is that for like a management unit which is normally a field, if you don't have precision irrigation practices ongoing, for one management unit, you should be able to develop these empirical relationships, tying ECE to ECA. And it might be the problem that when you have sinks and such, that then ECE, excuse me, the saturated paste extract is not the good measurement of salinity, really representing salinity as well. So you're always, this is like a proxy of the real salinity, which again is defined as the presence of soluble ions in the soil solution. And ECE is one of the ways to measure it, but again, it's an indicator rather than like a direct measurement of the chemistry of the soil, right?
Yeah, so next question is about what are the statistical parameters that we should take into consideration to select the better model to estimate soil salinity, and how can we select these parameters? So how to choose the best models and which criteria shall we use?
Well, once again, there are several examples in the literature with different types of modeling approaches. The modeling approach that we saw today keeps in mind the needs and constraints of having the need of getting like ground truth data sets with as few points as possible. And for that specific application, using ordinary least square methods is the way to go. Obviously, if you have other covariates that can be used, and not just the EM or like the ECA data, but you might have like another sensor, bare soil imagery, anything else that really helps you describe the spatial variability of soil, or like even the plant processes at the single site may help you increase the accuracy of this predictor. As well, you may want to include the X and Y coordinates to taking account of any drift of the data that you might have. But clearly, yes, that's the type of methodologies are the same. And one of the things that then can be done at the very basic level is to use, for example, backward stepwise type of methodologies to start from like a more numerous pool of potential predictors to learn to a more robust model with fewer predictors and so on. And as I pointed out here as well, if you have a lot of predictors, maybe hyperspectral data, you can use either principal component analysis or perhaps partial least square regression methods to use like hyperdimensional type of data sets for these type of methods. But again, the approach should be of selecting representative locations and making sure that they are spatially distributed in a manner to support the type of modeling that you're deciding to undertake.
Yeah, and so the question about using other software, statistical software like SPSS, GAMS. So is it possible to use other?
I mean, what we looked at today was a very simple regression method. We don't use Excel in our labs. Rather than doing preliminary data analysis, all of my team members nowadays use Python and R for most of the analysis, of course. And yeah, so we just looked at it at Excel because it's very visual, very easy, and most of the people have access to similar tools and don't require coding and knowledge to get it worked out. But obviously, a regression model is fairly universal for the different types of software, indeed.
Yeah, so regarding the software, it was a question about the remote sensing data. That is special equipment, particularly in terms of RAM, required for satellite data processing and the time series analysis. So is there a special software needed?
Yeah, it's a very good question, as a matter of fact. So the example that we looked at was done in MATLAB. Nowadays, most of the team members that I have are handling big satellite data with Google Earth Engine. But typically, when you are working with just the ground truth samples, you end up having like not such a big data set that you can do everything on a single machine using R or Python. When you want to extrapolate or apply those models over a big area, that's when you need to use cluster machines and so on. But yeah, so like for the calibration over hundreds of pixels, having like time series of a few years, I would suggest that a single machinery with fairly modern machinery could handle the computing necessities for that.
Yes, then the question, so we develop a new soil sensor for determining apparent electrical conductivity, and so they developed by their team. And can we use the same method for calibrating these measurements with laboratory saturation extract space?
Yeah, I don't see why not. Congratulations on making a novel sensor.
Yeah. So then next, the question, I would say that maybe it would be useful to explain more. So this ECA value, which you call proximal data, so which you measure with the sensor, is it primary or secondary data? I think that this question is more about what you mean by proximal data, and what is the difference between proximal data and sampling, soil sampling.
Yeah, proximal or no proxy, proxy, not proximal. That's I think that's what the question relates to. So this is proximal sensing means near ground sensing are all sensors that can be on a UAV, drone, or mounted on a tractor, walked on the ground. So they're not destructive of the soil, but they are not in space. Whereas the remote is more of an indication of data collected with satellite data. when we talk about proxy, we indicate a variable or like a measurement that is an indicator of our target soil process that we want to map, but is not a direct measurement and needs to be statistically calibrated or like calibrated with some sort of model to go from the information that is given by a sensor, let's say, or to the actual value that is interesting for agronomic decision making or the soil scientist in general.
Yeah, another question was about remote sensing, was related to using salinity indices, which it seems that you did not use them, right, in your publication. So the people are interested. So
Now,
that it is recommended to use salinity indices from remote sensing data and time series for mapping salt affected soils. And so I mean that. Did you use them, and if not,
oh
why?
yeah, we tested that. So we presented 3 on this discussion here, but obviously we like you know, whenever I have a student that does an analysis, I'll at least test 4 spectral indices to start with. One note on a lot of the spectral indices for salinity index, like that are called salinity index this, salinity index that, very useful tools. Obviously, they are based on the same bands that we used in the other one. So like they are one, recalculation of the bands that are also used in the indices that we looked at. And I'm calling them spectral indexes because in most cases they were developed to map surface soil salinity. Whereas the target of our exercise today and all the work that we do is to monitor plant performance over time to infer the salinity levels from that. So we used vegetation indices that are meant to look at the canopy performance. But when salinity indices were used, like fairly similar results were obtained. Yeah.
So now the opposite question about using the vegetation indices, that when you use vegetation indices for measuring or predicting salinity, actually vegetation state of vegetation is controlled not only by salinity. Mm-hmm. So actually there is no more, there is no, rather not question, but like.
No, but yeah, but that's exactly why we conclude that, and we recommend that if not a single image should be used, right? Because if you use just one snapshot, you may have salinity determining field at a flowering stage for a crop in one field, whereas the field nearby is at a vegetative stage or just a emerging stage, and there might not be salinity there. And you have low vegetation indices in both. So yeah, that's why we use time series data, and that's why we use multiple year time series data to sieve out other potential effects on crop that are not salinity. That was the scope of the exercise today, and the seminar last week. So vegetation monitoring is only feasible if time series analyses are used.
Yeah. So then one question regarding the practical use of the data that we receive. So we have the sensors, we have remote sensing, proximal sensing, all these calibrations. And the question is, then the farmer has this detailed map of soil salinity, and what can he do with this map? And do you have examples of the practical use of these detailed maps by the farmers?
Yeah, of course. Well, that is dependent on your agricultural system. Here in California, we use these maps for making sure that the leaching targets that the farmers have for their fields are met. So we talked about last week, as a matter of fact, about vegetable crop production. We want to make sure that there is when we do leaching in winter time, that we lower salinity at levels that allow crops to be grown with the target yield goals. and that we keep the salinity levels of sites that we might need to retire for, or like put or pause production for maybe one growing season or two growing season under control, so that then we know how much water we need to add once we decide to bring back those fields into production. So monitoring salinity means having a better control on the water that needs to be used to control such salinity to allow production of crops in those lands.
Then the question, can this approach be used for arid mountainous soils, the soils on the mountains? What do you think?
I would I think like the basic concepts probably, but definitely there are several processes playing a role in those environments there. So like we might need to carry out specific modifications to adapt to those systems. But the overall message here is that the processes that we like, the approaches that we are recommending are not just data-driven and statistically based and blindly trusting the statistical methods. What we recommend is to try to understand the system that you're working with, and they have like educated guesses on the expected processes that you will be dealing with, and try to use statistical as a tool to help you interpret those, rather than just going blindly and using statistical methods to create maps.
Yeah, so and now the last question for our participants, so that they can then use the webinar. Can we share this Excel table so that they can train themselves after the meeting? And
yeah, we can. I believe like the videos will be added on the FAO web pages, right? We can add like the georeference tables that we were looking at for sure.
Okay, thank you. That's all from my side. Jorge, over to you.
Thank you, Maria. Well, Dr. Scudiero, well, I wonder if you can recommend a good paper for the spatio-temporal kriging and other approaches, because you mentioned, and it is sound, that a multi-temporal examination gives better how to say, idea of what is the salinity. And then, so such procedure of making such interpolation using spatio-temporal data, I think that is the way. And so could you share some, or maybe later, could you share some publications that can orient? Yes.
We can add them like in the description of the page. I at the top of my hand, like I mean, for kriging methods, I think about like work coming out of Wageningen. That is always like a good reference for this. But we have like the simplified linear models as well, using analysis of covariance that we use here for like always like based on the minimal data, ground truth data. We have a couple of publications on those as well for monitoring salinity over time. Definitely, it is no longer the case that, or very rarely the case that you, as a soil scientist or a practitioner, will go and survey just one site. And that used to be the case that we would just do one survey, one map, and forget about the data. But nowadays, we can leverage the data sets from any work that was done in the past by open data sets. As a matter of fact, the UC Salinity Lab has one open data set for hundreds and hundreds of surveys that I would actually link for the viewership to use as an example, rather than the Excel table that I had, so that you can perhaps use hundreds of fields for training rather than a single field. But yeah, because we have, and if you are going into this enterprise as a government, maybe going to start to do a program, a water district will start a program, you can look into models that allow you to leverage this data over multiple fields. Mixed models, if you want to use linear models, or machine learning, can be very, very useful for that. Obviously, we cannot talk about those without understanding the processes behind all these practices, as we've done in these two webinars for this week and last week. But that's what we are doing nowadays. We are using machine learning to predict over space and time using these big data sets, and data assimilation, which meaning every time that we are doing a new survey, we recalibrate the models for the past surveys, and we give a better interpretation on the past models, but as well we leverage that past data set to strengthen models at any new field that we survey.
Yes, and finally, excuse me, I think that attendants will be happy to know that if you find some property of the soil that is correlated as well with the electrical conductivity, that you have focused on this electrical conductivity today. But if you find some variable of interest, this can be predicted as well from the measurement, like boron and selenium or others. I think it is the case. Can you please tell us?
Oh yes. So obviously there are several aspects that need to be included in this consideration, which is we show that there are some physical relationship between the sensor and the soil that is measured. So there are some soil properties that are measured directly, such as like the water content, the salinity, and then some other properties that may be measured directly, or just may be very well correlated at the side with the measure that you're taking. So in most cases, perhaps like you might be able to map cation exchange capacity that is not maybe measured directly by the sensor, but might be inferred from the data set, just because it has like a local correlation with the sensor measurement. And that's actually pretty powerful, because in most cases at the field scale, you have a lot of collinearities between processes. So we talked about boron, we talked about, like, we didn't talk about, but the selenium is another thing that we sometimes map in California soils. But particle size fraction, gravel content, the soil depth, a lot of these things are measured by can be mapped via electrical conductivity measurements. And the thing that the fact that they are often correlated at the field scale is a good thing for the soil scientists, because it makes things easier. The problems come when we have those cases where there's not collinearity between the soil properties at the field scale. That's when we need more soil samples, or like slightly different approaches for mapping, because that's where the sensor measurement is not as straightforward or like a direct proxy for the soil properties that we want to map. But to add one last thing, ECA as a sensor measurement is the probably most popular measurement taken for precision agriculture globally. And most of these measurements are taken not in salt-affected soils. And here, in those soils, and those scientists and those practitioners that are taking ECA measurements, they do it to map the water holding capacity or particle size fractions of the soil, maybe even organic carbon if it correlates well with the other soil structure properties. So it's a tool to show variability at the field level, and because it can be applied for so many different soil properties, taking soil cores to have like a quantitative indication of soil parameters is suggested.
Thank you very much, Dr. Scudeiro, for your very interesting and excellent presentation. Well, I observed in the chat and that people is really appreciating your presentation and content. And I think that it is of a high level and high interest, and practitioners will understand some of the aspects that make possible to use this technology, this approach. And also, as you mentioned it, that the technology is not so is quite affordable, because devices are now cheaper and cheaper, and GPS you have in telephone now with precision enough, good enough for making such maps and so on. So thank you very much. I think it was excellent, how to say, capacity building for the network. And we wait for you for next year. You will present us this as SAP new version that will be very interesting to understand how to choose the core sampling for validation of the models. Thank you very much. And so you are asked to join us next year with this when ready.
Thank you so very much.
So thank you, dear attendants, dear colleagues. And with this, we finish this webinar by today. And be attentive, because other webinars will follow in the next week. You will be notified through the email list of Dr. Maria Koniuszkowa will update you soon. Thank you very much to all of you, and thank you for attending this meeting.
Thank you all, and goodbye.
Bye-bye.